Hello everyone. So last time we were looking at how to solve an ODE, in particular second order ODE using power series method. Last time we considered an ODE, second order ODE in the form of, let's say, P of x y double prime plus Q of x y prime plus R of x times y equals 0. And assumed that x equals x naught is an ordinary point for this ODE. Then as a solution for this ODE, we considered a power series of the form y equals sigma an times x minus x0 to power n, and from 0 to infinity. And in order to find the coefficients AS, we substituted back into the ODE. And we found the recursive relation for AN first. So we found a recursive relation for AN. The recursive relation for AN by substituting into the original ODE. And then we found these coefficients using this recursive relation. So the recursive relation gives the value of AN in terms of the previous indices. So AN plus 1, for example, in terms of AN, or AN in terms of AN minus 1, or AN in terms of AN minus 1 and AN minus 2. So that's how a recursive relation looks like. And then we can find all ANs in terms of A0 and A1. For example, in this case of second order ODE, we need two arbitrary constants. So those could be our A0 and A1. And then we can find everything else, all the remaining coefficients in terms of A0 and A1. And then used it to find all ANs in terms of A0 and A1. And then we will have our general solution. Once you have all the coefficients in terms of A0 and A1, we can substitute into this equation y equals sigma an x minus x0 to power n. And then you will have a function, a linear combination of two functions, a linear combination of two linearly independent, basically, functions like A0 times a function plus A1 times another function. And that will be our general solution for this second order ODE. In particular, the last example we did last time. So last time we considered this equation y double prime minus 2xy prime plus 2ly equals 0. And after some calculation, we saw that we can consider y equals sigma an x to power n, and from 0 to infinity. And then the recursive relation would look like as follows. We would have a 2, A2 equals minus L A0, and AN plus 2 equals 2N minus 2L times AN divided by N plus 2 times N plus 1, with N bigger than or equal to 1. So N equals 1 or 2 all the way to infinity. And here, L here is a positive integer. L, positive integer. So now we can use this recursive relation to find all the coefficients. So we already have A2 in terms of A0. Then we can use the second equation to find A3, and then A4, and so on. So if I replace N with 1, then I'll have A3 equals 2 minus 2L times A1 divided by 3 times 2. Just replace N with 1 in this equation. Then I'll get A3 equals 2 minus 2L times A1 divided by 3 times 2. If I replace N with 2, then I'll have A4 equals 4 minus 2L, A2 divided by 4 times 3. And similarly, if I replace N with 3, then I'll get A5. Before calculating A5, let me simplify this first, because A4 equals 4 minus 2L times A2 divided by 4 times 3. But then A2 itself is minus L A0. We have it here. And 4 minus 2L, I can write it as 2 times and 2 minus L. And A2 is minus L A0 divided by 4 times 3. And if I want to write the denominator in terms of factorial, I need a factor of 2, because denominator would have been 4 factorial if it's multiplied by 2. So why don't I multiply top and bottom with 2, and then denominator becomes 4 factorial. So I can write this one as 2 to power 2 times 2 minus L times minus L A naught divided by 4 times 3 times 2. Which is same as 2 to power 2 times 2 minus L times minus L A naught divided by 4 factorial. And then what about A5? Now let's replace N with 3. If I replace A with 3, A5 would be 2 times 3 minus L over 5 times 4, A3. Replace N with 3, numerator here becomes 6 minus 2L times A3. 6 minus 2L means 2 times 3 minus L. And denominator would be 5 times 4. So 2 times 3 minus L, A3 divided by 5 times 4. And now what is A3? A3, we have it here. It's 2 minus 2L, A1 divided by 3 times 2. And 2 minus 2L, by the way, can be written as 2 times 1 minus L. So if I replace A3 with 2 times 1 minus L, A1 divided by 3 times 2, then I'll get 2 to power 2, 3 minus L, 1 minus L, A1 divided by 5 times 4 times 3 times 2. And this can be written as 2 to power 2, 3 minus L, 1 minus L, A1 divided by 5 factorial. Now if I continue this process, we observe that A to K will be equal to 2 to power K minus L, 2 minus L, all the way to 2K minus 2 minus L times A0 divided by 2K factorial. See if the index is even, like A4. Look at what we have for A4. It's 2 to power 2, which is half of 4. So if I call this one 2K, then the power of 2 will be K. And I will have minus L, then 2 minus L. So see, only even numbers would appear. All the way to all the way to the even number before 4. So if you continue right now from this term, we cannot see the pattern, whether this number 2 here is because it's half of this, or is it because this number minus 2. But if we continue this and write A6, you will see that for A6, this number here, the last number here that would appear would be 4 minus L. And 4 is not half of 6, it's instead 6 minus 2, the even number before the number that is appeared here. So what I'm saying is that here you can observe 2 2s, one 2 here, 1 2 here. But this 2 is basically the 2 that is appeared as a number that is half of this number. But this 2 is appeared because it's the even number before 4. And only for 4, these two numbers happen to be the same. But how can I know this? I'm saying that if you write one more term for A6, you will see that this number becomes 3, which is still half of 6. But then this number becomes 4, which is not half of 6. It's instead the even number before this index. All right, so this is the pattern that you'll be able to see. Once you write more terms, for example, once you write A6, you can see that this number here is always half of this index. Then I'll have minus L, 2 minus L, all the way to the even number before this number. The last even number before 2K is 2K minus 2, and then minus L times A0. And denominator always, this number matches this number. So if this is 2K here I will have 2K factorial. So here you saw that we had 4 here, and here we had 4 factorial. And so this is for A2K. What about A2K plus 1? So A2K plus 1 would be 2 to power K times 1 minus L, 3 minus L, all the way to 2K minus 1 minus L, divided by 2K plus 1 factorial times A1. So here, for example, 5 was 2 times 2 plus 1. That's why 2 appeared here. And what about these numbers here? Start with 1, then it goes all the way to the last odd number before this number. So 3 is the last odd number before 5. So for 2K plus 1, starts with 1, then 3 all the way to the last odd number before 2K plus 1 is 2K minus 1, and then minus L, A1. And this denominator here always matches with this index. So if it's 2K plus 1 here, 2K plus 1 factorial here. So here, for example, we had 5 here and 5 factorial here. So these will be the even indices and odd indices that can be computed this way. And then we can, now that we have all the coefficients in terms of A0 and A1, we can write the general solution. So hence, the general solution can be written as follows. So what was general solution? It was y equals sigma an x to power n, and from 0 to infinity, which is same as A0 plus A1x plus A2x squared, A3x cubed, and so on. Now I can write this one as A0 plus A1x plus, what would be A2? A2, if you remember, was minus LA0. I can also write this one as 2 times minus L divided by 2 factorial A0. So basically, I'm just saying that I'm allowed to multiply and divide this number by 2 and then write it this form. Why did I do this? Because I wanted to be consistent with the remaining terms, with the remaining even indices. Because for even indices, we had like 2 to some power times minus L all the way to 2K factorial here. So I want this index and this denominator match. So here, if I had 2 here, I want the denominator to be 2 factorial. So once I divide and multiply by 2, then this index will be also matching with the remaining even coefficients. So then I'll have plus 2 times minus L divided by 2 factorial x squared. And then plus, now for A3, what do I have? 2 times 1 minus L divided by 3 factorial. So I missed A0 here. A0 x squared plus this times A1 x cubed. And then for x to power 4, we have 2 to power 2 minus L, 2 minus L, a0 divided by 4 factorial x to power 4. And then for a2k, we had it here, 2 to power k minus L, 2 minus L, to 2k minus 2 minus L divided by 2k factorial a0 x to power 2k, so because this is a2k, so it's coefficient of x to power 2k. And then the next term would be a2k plus 1, which is the coefficient of x to power 2k plus 1. So I will have 2 to power k minus L, 1 minus L, 3 minus L, all the way to the last odd number before 2k plus 1, which was 2k minus 1 minus L divided by 2k plus 1 factorial a1 x to power 2k plus 1. Now I can factor the terms with a0 all together and factor terms with a1 all together. So I can regroup this term with this term, with this term, with this term, and regroup this term with this term, this term, all these terms together. Then I can write it as a0 times 1 plus 2 times minus L over 2 factorial x to power 2, 2 to power 2 minus L, 2 minus L, 4 factorial x to power 4, and then all the way to 2 to power k minus L, 2 minus L, 2k minus 2 minus L, x to power 2k divided by 2k factorial plus a1 times, so these are the terms with which are a multiple of a0, and then the terms that are multiple of a1 times x plus 2 times 1 minus L, 3 factorial x cubed, and then all the way to 2 to power k, 1 minus L, 3 minus L, 2k minus 1 minus L divided by 2k plus 1 factorial x to power 2k plus 1, and then plus the remaining terms. Now I can call this function here, if I call it y1, let's say, a0 times this big function, I can call it y1, and a1 times this function, big function, I can call it y2. So I can call it a0 times y1 of x plus a1 times y2 of x. Where y0 of x is this function here, 1 plus 2 times minus L, 2 factorial x squared all the way to 2 to power k minus L, 2k minus 2 minus L, 2k factorial x to the power 2k, and y1 of x is x plus 2 times 1 minus L, 3 factorial, x cubed, all the way to 2 to the power k, 1 minus L, 3 minus L, to 2k minus 1 minus L, 2k plus 1 factorial, x to the power 2k plus 1. And then plus the remaining terms. Now note that y1 of x and y2 of x are linearly independent. So here we have y as a linear combination of these two linearly independent functions. So this is y0 of x, and this is y1 of x, and we have y as a linear combination of these two. The general solution is linear combination of these two linearly independent functions. And why are they linearly independent? It's very easy to check, because if c1 y1 plus c2 y2 equals 0, then I'll have c1 times y1 is 1 plus 2 times minus L divided by 2 factorial x squared. C2 times y2, which is x, plus 2 times 1 minus L over 3 factorial x cubed. If this is equal to 0, then I can say c1 plus c2x equals 0. Now right hand side is identically 0, it's the constant function 0. So left hand side must be identically 0 as well. So by comparing the coefficients, I can say that the constant term must be 0 and the coefficient of x must be 0, and so on. So by comparing coefficients, comparing the coefficients, we can say that C1 must be 0, C2 must be 0, and that's all I need. I want to say that C1 and C2 are 0 in order to be able to conclude that Y1 and Y2 are linearly independent. I just need to say C1 and C2 are 0. Here, this C1 and this C2 must be 0. And once I put this linear combination equals 0, then I'll have this expression equals 0, which means the constant term must be 0, coefficient of x must be 0, and every other coefficient must be 0 as well, but I don't need them. I just need to use these two terms equals 0, because that already gives me a C1 equals 0 and C2 equals 0, and that's all I need. So I don't even need to use the fact that other coefficients are 0 as well. Only the fact that the constant term and the coefficient of x are 0 suffice to conclude that C1 and C2 are both 0, and therefore y1 and y2 are linearly independent. So y1 and y2 are linearly independent. So that's one remark that I wanted to say. And we had the general solution here. We found the general solution. We verified that y1 and y2, these two functions are linearly independent. One more remark that I want to say here is that the note if L is a positive integer, then either y1 or y2 will be a polynomial. See below. Remember, we assume that this L here that appears in our solution is a positive integer. Now I'm saying that once we assume this, then either y1 or y2, I call them y1 and y2. Sorry, not y1 and y2. Then either y1 or y2 will be a polynomial. Right now, they are written in the form of a series. Because I have, an infinite sum here and infinite sum here. So this is a series, this is a series. But I'm saying that once I assume L is a positive integer, one of these two will become a polynomial. Let's see why. So L is a positive integer, so it's either an even number or it's an odd number. So by assumption, L is a positive integer. So either L is odd or it is even. Now, if L is even, say L is equal to 2s or some integer s. Then what can I say about a 2s plus 2? Look at this formula here. We found a2k previously. If you look at this formula a2k, now what can I say about a2s plus 2? 2s plus 2 means the value of k would be s plus 1. So 2 to the power s plus 1. All the way to the last number appearing here would be the last even number before this index minus L. So if this index here is 2s plus 2, the last even number before 2s plus 2 is 2s. So I would have 2 to the power s plus 1 here. 2 to the power s plus 1 times minus L all the way to 2s minus L, a0 divided by 2s plus 2 factorial. So let me call this formula that I'm using, let me call it formula star. I will have this, but L is 2s. So 2s minus L is 0. And if this is 0, 0 times anything is 0, and therefore a to s plus 2 will become 0. A to s plus 2 becomes 0. Now that I know a to s plus 2 is 0, what can I say about the next even indices. Thus, a 2s plus 4, which is some constant times a 2s plus 2 is 0 as well. See, we had an plus 2, if you remember, an plus 2 was some constant times an. So every index can be written in terms of two indices before. An plus 2 is the constant times an, two indices before. So a to s plus 4 would be a constant times two index before, which means a to s plus 2. But a to s plus 2, we just showed it's 0. So a to s plus 4 will be 0 as well. Similarly, a to s plus 6 will be some constant times a to s plus 4, which is 0. Now, what will be y1? If you look at y1, it's the addition of all even coefficients times x to even powers, apart from the factor a0, because a0 has been taken out and is not part of y1. So we can say that y1 is 1 over a0, because a0 has been taken out, times a0 plus a2x squared, a 4x to the power 4, all the way to a to s, x to the power 2s, plus a to s plus 2, x to the power 2s plus 2, then a to s plus 4, x to the power 2s plus 4, and so on. Now this term is 0, this term is 0, and every next term is also 0. A to s plus 2, 2s plus 4, 2s plus 6. All the even numbers after 2s plus 2 are 0. The coefficients with even indices that are after 2s plus 2 are 0. So then we'll be left with 1 over a0 times a0 plus a2x squared plus a4x to the power 4, all the way to a2s x to the power 2s, and this is a polynomial. So in the case that L is an even number, y1 turns out to be a polynomial. Similarly, you can check as an exercise that if L is an odd integer, then y2 is a polynomial. So we found two linearly independent solutions for this ODE. And as long as L is a positive integer, one of these two solutions becomes a polynomial. If L is an even integer, y1 becomes a polynomial. If L is an odd integer, y2 becomes a polynomial. All right, so in this topic, one of the most challenging tasks is to find the recursive relation for an. Once we find the recursive relation for an, then everything else will be straightforward. So let me give you one more example just to focus on how to find the recursive relation. So example, suppose that sigma an times n squared plus 1 times 3n times x to power n minus 1, and from 3 to infinity plus sigma a n plus 1 times n plus 2 times n minus 1 x to power n, and from 0 to infinity plus sigma a n times n minus 4 2 to power n times x to power n plus 1 equals 0, and again from 0 to infinity here. Find a recursive relation for an. Find a recursive relation for an. So here, see, the powers do not match. The starting indices also do not match. So that's where the issue is. If the powers match and the starting indices match, then it would be easy to handle. But what should we do now that the powers and the starting indices do not match? Well, in the previous example, we said that, why don't we think about each of these sums as like the starting term? What is the starting term? Is it the constant term? Is it the x term? Is it the x squared term? What is it? So let's think about this for each of these sums. For the first sum here, because it's n minus 1 and n starts from 3, so the first term will be x squared term. Because it's n minus 1 and n starts from 3, so the first term will be x to the power 3 minus 1, which is 2. So the first term will be x squared term, then some constant, then something times x to the power 3, and so on. So this one starts with x squared term, and then something times x cubed, and so on. Now, what about the next sum? If you look at the next sum, it's x to the power n, and n starts from 0. So the first term will be x to the power 0, which means a constant term, and then the constant term, and then something times x, plus something times x squared, and so on. What about the next sum? It's x to the power n plus 1, and n starts from 0. So the first term will be x term. If you replace n with 0, it will be x to the power 1, which means x term, and then x squared term, and so on. So then the next sum here will be something times x plus something times x squared plus so on. So when I consider all together, so constant term and x term must be separated because, for example, this sum have no constant term or x term. So I have to separate constant term and x term from these sigmas. And then starting from x squared term, I can combine these 3 sigmas because all 3 of them have x squared term, x cubed term, and so on. So starting from x squared term, I can combine these 3 sigmas. But before that, for the constant term and x term, I have to separate them because this sigma does not include any constant term or any x term. And this sigma doesn't include any constant term either. So let's separate the constant term and the x term. So then what do we get? So sigma, and let's replace everything else from, let's say, in the form of x to power n, and from 2 to infinity. because constant term and x term will be separated. And then starting from x squared, I can write it as x to power n from 2 to infinity. So how can I do that? I just need to replace n with n plus 1 here, and then I'll have x to power n. So for the first time, I can replace it n to n plus 1. Then I'll have a n plus 1, n times n plus 1, the whole squared, plus 1 times 3 times n plus 1, x to power n from 2 to infinity, because I've changed n to n plus 1. The starting index will shift 1 unit to the left. Now that's for the first sum. For the second sum, we said we have to separate constant term and x term. So n equals 0 corresponds to the constant term. If I replace n with 0, I'll have a 1 times 2 times minus 1. So I have to separate that term. So plus a 1 times 2 times minus 1. And then n equals 1 term, and I mean x term, which corresponds to n equals 1. So a2 times 3 times 0. Now anything times 0 will be 0. So I can just delete that term. So x term, the coefficient will be 0. And then I can write it from 2 to infinity, x to something times x to power n, which means x squared and everything, which include x squared and everything after that, like x cubed, x to power 4, and so on. So plus 0 plus sigma an plus 1 times n plus 2 times n minus 1 x to power n, and from 2 to infinity. So this sigma started from 0 to infinity. I separated n equals 0 and n equals 1, which correspond to constant term and x term. And then the rest of the terms, I can write it as a sigma starting from 2 to infinity of this term. I don't need to change n to n plus 1 or n minus 1 because the power is already n. Now for the third sum, start from x term. We said we are going to separate the x term. So n equals 0, because x term here corresponds to n equals 0, because it's the power is x to power n plus 1. So if I replace n with 0, I will have x to power 1, which means x term. So n equals 0 has to be separated. And then I'll have a0 times minus 4 times 2 to power 0. So plus a0 times minus 4 times minus 4 times 2 to power 0 x. And then I have to write the rest as a sigma. So plus sigma n from 1 to infinity of this term, an n minus 4, 2 to power n, x to power n minus 1, n plus 1 equals 0. So for the third sum, the only thing I did, I separated x term, which correspond to n equals 0, and then I wrote the rest of the terms in the form of a sigma, and from 1 to infinity of the same expression. Now here I have something times x to power n, and from 2 to infinity, something times x to power n, and from 2 to infinity. But this one is something times x to power n plus 1, and from 1 to infinity, which can be easily matched with these two. I just need to replace n with n minus 1, and then the power becomes n here, and the starting index will be 2 to infinity, because if I change n to n minus 1, the starting index, we know that it will be shifted 1 unit to the right. So this sum is same as sigma n from 2 to infinity of a n minus 1, n minus 1 minus 4, 2 to power n minus 1, x to power n. If I replace n with n minus 1, starting index will be shifted 1 unit to the right, and then I'll have this. So what can I say? So the constant term here, I have a constant term, minus 2a1. Minus 2a1 is the constant term. X term, I have only one of them here. And then I can combine these three sigmas together. So minus 2a1 minus 4a0 x, and then sigma n from 2 to infinity. Now I can combine these three sigmas together. For the first one, I have a n plus 1 n plus 1 squared plus 1 3 times n plus 1 For the second one, I have a n plus 1, n plus 2, n minus 1. For the third sum, I have a n minus 1, n minus 5, 2 to power n minus 1. X to power n equals 0. And now to find the recursive relation, I can simply compare the coefficients in the left-hand side and right-hand side. So by comparing coefficients, right-hand side, I have the constant function 0. So left-hand side, every coefficient must be 0, which means constant term must be 0. And then coefficient of x minus 4a0 must be 0. And then coefficient of x to power n for n bigger than or equal to 2 must be 0. So a n plus 1 times n plus 1 squared plus 1, 3, n plus 3 plus a n plus 1 times n plus 2 times n minus 1 plus a n minus 1 n minus 5, 2 to power n minus 1. This has to be 0, which will be valid for n bigger than or equal to 2. So minus 2a1 equals 0 means a1 is 0. Minus 4a0 is 0 means a0 is 0. So I can say a1 equals a0 equals 0. And a n plus 1 equals, now this equation, if I take this term to the right-hand side, then becomes 5 minus n times 2 to power n minus 1, a n minus 1. I took this term to the right-hand side, and it grabs an extra minus. And these two terms, I can factor from a n plus 1. So a n plus 1 times this plus this will be minus this term. which means an plus 1 will be minus this term divided by this plus this. So divided by n plus 1 squared plus 1 times 3n plus 3 plus n plus 2 times n minus 1. And this will be valid for n bigger than or equal to 2. So for n bigger than or equal to 2, this will be our recursive relation, and a1 and a0 have to be 0. And this is all we have to do because the question was asking us to find a recursive relation for an. So this is a recursive relation for an.